Imagine yourself standing on the surface of Mercury, but not the Mercury you usually picture. Not the blazing furnace of daytime, where the sun scorches every inch of the barren planet. No. This is a night so long it feels eternal. A night that began weeks ago, and will stretch on for weeks more. Above you, the stars burn sharp and cold, like diamonds scattered across a curtain of flawless black velvet, untouched by any hazy atmosphere. The ground beneath your thickly insulated boots is like frozen stone, silently bleeding the last whispers of warmth into the endless void of space. Everything is still, as if the planet itself has forgotten how to breathe. But tonight, you are not just here to survive. You came prepared. You brought with you a special instrument, a sensitive detector attuned to a hidden wavelength of light. And slowly, you lift it, pointing it toward the anti-solar point in the sky. That direction was exactly opposite to where the sun quietly hides beneath the horizon. And then, you see it. Something faint, fragile, almost too unreal to believe. A silent and elongated glow, like a whisper from the invisible realm, gently stretching out from the planet, reaching so far into the darkness it seems untouchable. It's a mystical structure, invisible to the naked eye, yet it's there. Slender like the trailing silk gown of a ghostly dancer from another world. A delicate streak of light, stretching for millions of kilometers, clinging behind the small, battered world named Mercury. In this seemingly frozen darkness, Mercury, the little planet thought to be inert and lifeless near the sun, is performing something deeply strange. It's releasing a tail into space, but not of dust or gas, like the comet tails we're used to seeing, but something far more special, far more captivating. Sodium atoms. Today, join me in exploring one of the most subtle and surprising phenomena in the solar system, the vast, invisible sodium tail of Mercury. We'll trace the steps of its strange discovery, investigate the complex processes that form and shape it, and listen to what this ghostly appendage reveals about the innermost planet and its unique, haunting bond with the sun. When we think of planets with distinct features, Mercury rarely comes to mind. It's the runt of our planetary family, a tiny cratered world baking under the unforgiving sun. But in 2001, everything changed. Since the mid-1980s, scientists had been using specialized sodium filters to observe Mercury, after detecting sodium in the planet's exosphere. And that's exactly what the team at the McDonald Observatory in Texas was doing, when they noticed something odd. A faint glow, extending far beyond Mercury's tiny disk. At first, they didn't trust what they saw. It had to be a glitch, a hiccup in the equipment or some flaw in the data processing. But after checking, and checking again, the astonishing truth came into focus. Mercury was trailing an enormous structure through space, a sodium tail stretching almost 2.5 million kilometers behind it. For context, that's 700 times the width of Mercury itself. The discovery was humbling. Mercury isn't some distant, obscure object. It's one of our closest cosmic neighbors, a world we've observed since ancient times, and even visited in the 1970s and 2000s thanks to NASA's Mariner 10 and Messenger spacecraft. And yet, this colossal feature remained completely hidden until the 21st century. The discovery was monumental, because it shook our understanding of which objects in the solar system can grow tails. Suddenly, Mercury was no longer just a bland, cratered world, but a planet with a dynamic structure that could rival the most breathtaking comets. So, what makes Mercury's tail different from those of comets? And why would this planet, of all planets, have a sodium tail specifically? The answer is the fascinating result of Mercury's unique position, its rocky composition, and the fierce grip of the sun's power. Comets, in a way, are like icy snowballs careening through space. They're mostly made of frozen water and gases, which sublimate into vapor as the comet nears the sun, leaving behind a glowing trail of ionized gas and dust. But Mercury isn't like that. It's a scorched, rocky planet with little to no ice. Some scientists believe there could be hidden ice tucked away in craters near the poles, places that lie in permanent shadow, untouched by sunlight. And it's precisely because these icy patches never see the sun that they remain frozen and undisturbed. So, Mercury's tail isn't created by sublimation. It's made of something else entirely. Sodium. But why sodium? To answer that, we need to consider Mercury's perilous closeness to the sun. At perihelion, Mercury swings as close as 47 million kilometers from the sun, where it's bombarded by solar radiation nearly 10 times more intense than what we experience on Earth. The solar wind there is not a gentle breeze, but a raging torrent of charged particles, constantly flying straight at the planet at speeds up to 1.6 million kilometers per hour. When these particles crash into Mercury's surface, they don't simply glance off. They knock atoms right out of the ground. It's a process called sputtering. Imagine a handful of fridge magnets clinging to your refrigerator. They stay put because the surface holds them tight. But now, imagine throwing a bouncy ball at the fridge. When it hits, energy ripples across the surface, shaking everything in its path. If that energy reaches one of the weaker magnets, with more force than what's keeping it attached, it pops off and falls to the floor. That's exactly what's happening to sodium atoms on Mercury's surface. That's exactly what happens in a sputtering collision cascade. Ions from the solar wind shower Mercury relentlessly, creating high-energy impacts that knock the weakest atoms loose from the planet's surface, just like the bouncy ball popped off the weakest fridge magnet. And as it turns out, one of the most weakly bound elements on Mercury's surface is, yes, sodium. Messenger data reveals that during periods of intense solar wind activity, these solar particles rain down on Mercury's crust, resulting in a 50% spike in sodium group ions in the planet's thin atmosphere. This suggests that stronger solar winds amplify surface particle interactions, leading to a greater release of sodium into Mercury's exosphere and trailing tail. But there's more to the story. Beyond the solar wind, Mercury is also tormented by micrometeoroids, and without an atmosphere to slow them down, even dust-sized grains slam into the planet's surface with staggering force. These tiny space rocks vaporize surface materials on impact, releasing even more sodium atoms into space. We're essentially witnessing a process of cosmic erosion, a planet slowly disintegrating over billions of years, right in our own solar system's front yard. Some researchers have observed enhancements in Mercury's sodium tail, seemingly coinciding with times when the planet passes through denser streams of interplanetary dust, such as debris left behind by comet Anchor. This temporarily boosts the effects of micrometeoroid impact vaporization, injecting more sodium into Mercury's exosphere, and ultimately feeding the trailing tail. But the shaping of Mercury's sodium tail isn't primarily due to the solar wind blowing it backward, as is largely the case for a comet's ion tail. Instead, the dominant force sculpting Mercury's sodium tail is solar radiation pressure, a subtle, yet profoundly powerful influence. Photons, though they have no mass, carry momentum. When a sodium atom in Mercury's exosphere absorbs a photon of light, it receives a tiny push in the direction that photon was traveling, away from the sun. The atom then quickly emits a photon in a random direction, causing an average recoil that is practically negligible. But almost instantly, it's ready again, ready to absorb the next photon coming from the sun. This continuous process, absorbing sunlight and receiving tiny directed nudges, acts like a soft yet persistent breeze, pushing the sodium atoms steadily away from the sun. Imagine countless tiny solar sails, each one a sodium atom, each one being endlessly nudged by the pressure of sunlight. This gentle but relentless force accelerates the atoms anti-sunward, overcoming Mercury's feeble gravity, and stretching them out into the vast ghostly tail that we can observe from Earth. Because radiation pressure acts directly away from the sun, the tail of Mercury consistently points in the anti-solar direction. But as I mentioned earlier, despite its enormous size, it's completely invisible to the naked eye. So, how did scientists detect it? When sodium atoms absorb energy, they become excited, meaning their outermost electron jumps to a higher energy level. When that electron falls back down to its ground state, it emits photons at a very specific wavelength, 589 nanometers. And the light at this wavelength has a color you've definitely seen before. It's the warm golden hue of old street lamps, the amber glow that used to bathe quiet neighborhoods in the night. This emission is happening constantly in Mercury's tail, yet the glow is too faint for human eyes or standard telescopes to detect. To reveal it, astronomers use specially designed filters known as sodium D-line filters. These filters isolate just the 589 nanometer wavelength, blocking out all others, allowing the delicate sodium glow to emerge against the deep black of space. By deleting all other wavelengths from their results, scientists were able to see Mercury's luminescent glow with stunning clarity. Surprisingly, deletion isn't just useful in science. It's incredibly valuable in everyday life, too. Your personal data is almost certainly floating out there, in public records, in every mailing list you've signed up for, and in every social media post you've made. That data can easily fall into the hands of data brokers, who buy and sell it to anyone, no matter their intentions. If you enjoyed this video, don't forget to leave a like and subscribe to join us on future journeys. Now, back to Mercury. By deleting all other wavelengths of light, scientists were able to clearly detect the sodium tail. And here's what's fascinating. That tail doesn't stay the same. It varies dramatically throughout Mercury's 80-day orbit around the Sun, which is highly elliptical. When Mercury swings around to perihelion, the increased solar radiation dramatically intensifies the rate at which sodium is ejected from the surface. You might expect the tail to be at its most visible right at perihelion, since that's when the solar wind and radiation are strongest. But surprisingly, the sodium tail actually reaches peak brightness 16 days later. Let me explain. Because Mercury's orbit is so elliptical. Its orbital speed changes significantly, from around 39 kilometers per second when it's farther from the Sun, to 59 kilometers per second when it's closest. Through repeated observations, scientists noticed that Mercury reaches its maximum radial velocity after slingshotting past the Sun, exactly 16 days after perihelion. In other words, that's when Mercury is moving away from the Sun at its highest speed, creating perfect conditions for the sodium tail to stretch out and shine more clearly. But why would a faster speed result in a brighter tail? 2 words: Doppler shift. When we we look at the spectrum of sunlight, we see dark lines scattered across it, called Fraunhofer absorption lines. These lines mark the specific wavelengths of light that are being absorbed by elements in the sun's atmosphere before the light escapes into space. One of those elements is sodium, the same element that fills Mercury's glowing tail. That means sodium-specific light from the sun is usually blocked, absorbed by the sun's own atmosphere before it even has a chance to reach Mercury. But the faster Mercury moves away from the sun, the more that sunlight becomes Doppler shifted, or stretched. This stretching shifts the entire light spectrum to longer, redder wavelengths, including the Fraunhofer lines themselves. And when that shift happens, the sodium-specific light is no longer blocked. It becomes available for Mercury's sodium tail to absorb and scatter. The result? The tail glows brighter. And from Earth, we can finally see it. So, if astronomers want to spot Mercury's tail, they just need to look up on day 16 after perihelion, right? Well, it's not quite that simple. There are 3 other major factors that come into play. First, Mercury needs to be at a sufficient elongation from the sun in Earth's sky, so that it isn't swallowed up by the sun's blinding glare. Second, Mercury can't be behind the sun from Earth's perspective, or it would be entirely out of sight. And third, it needs to be positioned at just the right angle, so Earth-based telescopes can view the tail stretching anti-sunward. This kind of perfect celestial alignment only happens during very specific windows, roughly every few years. And to think, the scientists at McDonald Observatory happened to catch it, almost entirely by chance. Now that's what you call perfect timing. Some of the most spectacular images of Mercury's sodium tail have come from observatories using coronagraphs, instruments that block out the sun's direct light, allowing the faint glow of the tail to shine through, even when Mercury appears close to the sun in our sky. Each successful observation is a triumph of astronomical precision and planning. These rare glimpses reveal a tail that's always in motion, stretching, contracting, brightening, fading, in a cosmic dance choreographed by orbital mechanics and atomic physics. But this story doesn't end with Mercury. It opens an unexpected window into the fundamental processes unfolding throughout our solar system and far beyond. But this story stretches far beyond Mercury itself. It has opened an unexpected window into the key processes unfolding across our solar system and well beyond its edges. First, it offers a glimpse into planetary evolution. While the current rate of surface material loss is too slow to significantly alter Mercury within a human time frame, over billions of years, this process could gradually reshape its surface chemistry, slowly depleting sodium and other easily liberated elements. We can use this insight to imagine what might have happened to ancient planets in distant star systems, and better understand their life cycles. Second, and perhaps most exciting of all, this discovery carries powerful implications for exoplanet research. Many star systems host what are known as hot Jupiters, massive gas giants orbiting scorchingly close to their parent stars. If Mercury, a small, rocky world, can generate a tail stretching 2.5 million kilometers, then these giant planets likely host even more dramatic features, potentially shedding significant mass through similar processes. The detection techniques refined to study Mercury's sodium tail are now being repurposed to hunt for comparable phenomena around distant exoplanets. By scanning for the distinctive spectral fingerprints of elements being stripped away, astronomers are gaining new insights into the composition and environments of alien worlds. In fact, similar sodium tails have already been detected around our own moon. suggesting that this phenomenon may be quite common, especially among airless bodies exposed to constant solar wind. Mercury's sodium tail is more than just a spectacle. It's a perfect laboratory for studying planet-star interactions across the cosmos. By deepening our understanding of this ghostly trail, we unlock essential clues about how stars shape, sculpt, and slowly erode their planetary systems over the course of billions of years. The BepiColombo mission has already completed 6 rapid flybys of Mercury and is set to enter orbit in December 2025. Once there, it will spend at least 1 Earth year studying Mercury's inner composition and its breathtaking exosphere. This mission will deliver data on Mercury's sodium tail in unprecedented detail, promising new insights into one of the most fascinating phenomena in our solar system. Mercury's elusive tail serves as a gentle yet powerful reminder that even after centuries of watching the skies, we're still uncovering fundamental truths about our closest cosmic neighbors. So what other secrets might still lie hidden in our celestial backyard? The universe never stops surprising us. All we need to do is keep looking. Though it's just a small planet orbiting close to the Sun, Mercury continues to surprise us with mysteries we never expected to find. Its invisible sodium tail isn't just a scientific curiosity. It's a quiet reminder that the universe still holds wonders waiting to be discovered. And every time we look up, the cosmos becomes just a little more alive in our minds. If you found this journey inspiring and fascinating, don't forget to like the video, share it with friends, and subscribe to the channel so you won't miss what's coming next.